half IT, sorry. See that I'm copying it correctly. Minus I pi over 8 times zeta 5/4 plus IT times 1 plus capital 1 over t. Forget about this. I'm going to get an upper bound for this. So forget about that term, but let me keep that. Consider the main term. So that's equal to this. So this is now 17 and this is 18. So consider the main term in 18, which is main term meaning without ignoring this. I'm going to choose the main term. So the main term, because of the zeta, I'm going to write it as summation n from 1 to infinity 1 over n to the 5/4. It's 5/4 plus IT, but I'm writing that n to the 5/4 plus IT as n to the 5/4 n to the IT. N to the IT at the bottom is e to the minus IT log n. So you will see, I mean, at this stage, when I apply lemma 4, you will appreciate the generality of the lemma where the bound does not depend upon A and B, and purely depends upon some lower bounds for derivatives and second derivatives. That will come in here. Okay, so it's n to the power 1/4, integral t to 2t, okay, of t over 2 pi to the power 3/8 plus it over 2 e to the minus it 2. I'm going to ignore this. That's a constant. That's just a constant which comes out. So if you want, you can put e to the minus 8. But most importantly, I get minus it log n. That may force some cancellation because log n tends to move, right? dt. All right, 19. Okay, now we invoke lemma 4. So at this stage, we invoke lemma 4. In what form? With. So I'm not going to tell you what f of x is. I did this calculation. Okay. With f prime of t, with f of t equal to 1/2 t log t over 2 pi. So how does that come? Yeah, this is for the f. This is g. I'm sorry. I'm focusing on the f. Go back to lemma 4. Lemma 4 is e to the I f of x. So whatever is attached to I is what I'm writing down here. Okay, so it's attached to e to the I. So this is the part involving I. So f of x is, you take this log. So log 2, so it's t over 2, log t over 2 pi, minus t over 2 pi, minus f of t is 1/2 t log t over 2 pi, where did I get the minus 2? That's minus t over 2, isn't it? It doesn't matter because I'm going to get f double prime. T over f of t is 1/2 t log t over 2 pi, correct? Minus I t over 2 minus t log x. That's what I mean. No 2 pi here. Sorry, made a mistake. So this is f of t. And what is g of t? G of t, or g of x, is just the real part. T over 2 pi to the power 8. All right. So that's your g. Now we calculate. So note that. Do f prime. I want to get f double prime. So what is f prime of this? Well, oh, okay. So I understand what I did here. Okay. So this is 1/2 t log t minus 1/2 t log 2 pi. That's what I mean. All right. So we first do f prime, and the derivative of t log t is log t plus 1, right? Log t plus 1. And these, I don't care. I mean, the derivative is half. This derivative is some constant. And this derivative is log n. Why is it I don't care? Because that lemma deals with f double prime. So f double prime is 1 over 2. That's all I need. F double prime is 1 over 2t. And that is greater than or equal to 1 over 4t. Now in that lemma, that's the r. That's the r in the lemma that I have to use. So now I have to get an upper bound for the integral. Okay. Thus, the integral in 19 is bounded by t to the power 3/8, or is less than, some constant. This is some constant. T to the power 3/8 divided by square root of 1 over 4t. That is equal to t to the power 7/8. But then I have to sum over the series. The series is convergent, and therefore we get that the entire, we get the upper bound or the integral over the vertical portion is capital O t to the 7/8. It's important that you get an exponent which is less than 1, because the next integral will be of size t. This integral is going to be of size t. And there is a very nice reason for that integral to be of size t. You will appreciate the cancellations that take place when I have imaginary exponents in integrals. Okay, so now let's go to this last one. This is a hard analysis. I mean, Hardy and Littlewood were masters of this. I remember once talking to actually somebody at the Tata Institute. And my Indian friend has left. She would appreciate what I say about the Tata. Maybe she should see the video too. And the Tata Institute people are great followers of the Bourbaki tradition. And so it's all abstract algebraic. And I remember one of them saying in the thing, oh, this is just Hardy-Littlewood analysis. What do you mean? Hardy-Littlewood analysis is very subtle and intricate. It's not easy. Not everybody can do Hardy-Littlewood analysis, right? How did he choose the function chi? How did he come up with these specific things? You know, it might not be abstract, but it is still deep. Okay. All right. So now we will see the other one. So now let us get to the second one. All right. Next we observe. We'll finish this in 10 minutes. There's only one little trick that we need. The integral from t to 2t of the absolute value of z of t dt is the integral from t to 2t of the absolute value of zeta half plus it dt. And we just use a crude lower bound to begin with, greater than or equal to the absolute value of the integral from t to 2t of zeta half plus it dt. Now this is very nice because I'm integrating now an analytic function. So I can get this integral, again using Cauchy's theorem, by going to the other three sides and by getting a lower bound on that. Okay, so we have this. All right. So this is now, so this is 21. Okay, so now let's make this 22. So now we say, observe that, so we finish soon. Observe that the integral from t to 2t, maybe I'm missing a factor of I. Very, very particular, put a factor of I here because of the change of variables. This is equal to the integral of 1/2 plus it to 1/2 plus 2it zeta s here, so that I can apply Cauchy. I think I'm missing a factor of I, right? This is an I integral. Okay. So this is equal to the integral from 1/2 plus it to 2 plus it plus the integral from 2 plus it to 2 plus 2it plus the integral from 2 plus 2it to 1/2 plus 2it. The usual thing. We go through the, but oh, by the way, you might say, why did I go to 2? Here it's easier for me to use n squared than n to the 5th order. I'm just going to get this. All right. So I went to n squared. All right. So now what can you say about this? This integral is over a bounded range. This integral is over a bounded range. They're horizontal integrals. The value of the Riemann zeta function is no more than zeta of no more than t to the 1/4. So the first, this integral and this integral yield capital O of t to the 1/4 plus epsilon. That's what we just proved. All right, so we got that. Now what about this integral? This is very interesting. This is integral from 2 plus it to 2 plus 2it of zeta s, which I now write as summation 1 over n to the s, n from 1 to infinity ds. And I want you to observe what is happening here. Separate out the first term in the series for the Riemann zeta function, and that is just 1. That will be the only thing that will contribute significantly to this integral. It's amazing. So, write this as capital O of t to the 1/4 plus epsilon plus just the term corresponding to n equal to 1. The term corresponding to n equal to 1 is just the integral from 2 plus it to 2 plus 2it of ds. And now write the series from 2 plus it to 2 plus 2it of summation 1 over n to the s from 2 to infinity ds. This is capital O of t to the 1/4 plus epsilon. This integral is just it's just an ordinary line integral, that point minus this point, so this is exactly it. And what about this? This is a summation from 2 to infinity, but now the n to the s, I can think of it as 2 plus I little t. So I pull out the n squared out. Or if you want to do it on the 5/4, you pull out the n to the 5/4 out, it doesn't matter. But now look at the integral. It is the integral from 2 plus it to 2 plus 2it. The ds is really a dt integral with an I coming out, like I came out here. But now the dt integral is, each term is like n to the power it's e to the power minus it log n, et. And what is the antiderivative of e to the power it log n? It's e to the power minus it log n divided by I log n, which cancels this I. So divided by log n. So this is equal to capital O. So this is somewhat unbelievable that it works so well, it plus summation n from 2 to infinity 1 over n squared, and you put a log n here. Now that's a convergent series. And inside I have the value of this function I capital 2t log n minus I to the t log n. What does it matter? The exponential function is bounded with the imaginary value is bounded by 1. So this is capital O of 1. This is the beauty of this. I mean, the fact that you have an n to the it forces this cancellation, so to speak. So the value at 2it minus the value, they're all bounded. And therefore, this series is capital O of 1 over n squared log n, which is a convergent series. So this entire thing is really O of 1. So this actually gives you it plus capital O of t to the 1/4 plus epsilon at the actual value, which means the absolute value of this is greater than or equal to t. 1 times t, or minus epsilon t. Therefore, the integral of the absolute value of z of t dt from t to 2t is greater than or equal to t minus capital O of t to the 1/4 plus epsilon. And hence, this integral is much bigger than this integral. Much bigger than this. This is no more than t to the 7/8, but this is at least as big as t. That proves Hardy's theorem. Okay, so this proves Hardy's theorem. Hardy was a super technician. I mean, there's no question about it. And that is why, even in this Ramanujan thing, Ramanujan saw patterns. Ramanujan could correctly identify which would contribute, which is fine. But one still needs to prove that what you identify as the thing that contributes is the one that really contributes and the others do not contribute. So some technical progress is needed to show that these other things can be controlled. And you see how beautifully that lemma 4 comes into the picture. See, when you start with this, f of t is big. So that's why I was a little bit surprised. I made one small mistake in my computation, but luckily it was an inconsequential mistake. The mistake was I did not have this extra term, but I really didn't need it because I'm taking second derivative, so it vanishes. So the real thing is only that. So the second derivative gives you 1 over t, and that's why it's big. Okay, so this proves Hardy's theorem. So on Monday, when we come in, I'll talk about something called the Lindelof hypothesis, and we'll talk about this convexity. There's a very famous theorem of Ingham, which says that if you have bounds for the Riemann-Zeta function on the half-line, those bounds yield gaps for gaps between consecutive points. So in that context, we will understand the Lindelof hypothesis and what it gives. And then Hardy, so what 1/4 gives. We already know bound for the Riemann-Zeta function on that line, so we'll use Ingham's theorem to get that. I won't prove Ingham's theorem, but these will be some comments. But then I will prove some oscillation theorems for error terms.